Okay, so good morning, everyone. I think for today's class, I will review some part of the exercise, chapter 4 and chapter 5, or chapter 6 if you have the new book. It's actually chapter 6. I just uploaded additional videos on chapter 4 exercise. So this will be the continuation of that video. And chapter 4 and chapter 5 or chapter 6, it will mostly it will be your final exam. So chapter 4 will be focused on the torsion, and if you look on the course that we have, I think I can tell you that the final exam will be focused on not only the introduction part in the torsion, but most likely I will focus more on the indeterminate structure. So suppose that like something like this, you have the attached to the wall, so you can focus more on so geometry wise or shape, you have figured out how the deformation will be. You can add the compatibility equations, which is the total of the twist angle or rotations will be 0, unless maybe there will be some questions or information given in the questions in the problems. Okay, let's try this one. We have this shaft. It's aluminum alloy, so it's all one specific material, which is aluminum. It has shear modulus 26. It has length, and then we have a segment BC, which is a solid segment. So the AB is a hollow tubular section, and BC will be solid. So the difference between solid and hollow will be the inertia. How to find the inertia? You have each own diameter, and then question asking the T1, T2, and internal torques in the two segments. T1 and T2. And then the second one is maximum shear stress, the tau max for element 1, element 2. And then the twist angle at B. Okay, twist angle at B. Now we can start with as usual, we can start with, we can draw the free body diagram. So because we are going to focus more on the point B, so I will cut off this part. Okay? So this one. So I will get the element 1 to compute T1 and element 2. So we can have, let's say, suppose this is the axis. Okay, and then this will be B in the middle. So this is the B. And then B, we have the torque, which is 10, right? 10 kilonewton external torque at section B. So here we have 10 kilonewton meter. And then we can add T1 and T2. It's actually based on your preference. Okay, we can have perhaps like this or like that. It not really that matter, because you will see that at the end of the day we can compute the torque, and if you get the result is negative, which means it's the opposite side. So suppose that we have this as this direction here. Let's say this is T1. Let me write here. This is T1. Oh, this is T1, and this will be T2. Now, based on what we have here, we get that T2 plus TB equal T1, or T2 is T1 minus TB. Okay, both we can use. And then what's next? Next is we can focus more on the inertia. So this is basically for most of the content. For the chapter 4, this is what we are going to make through. So first is equilibrium, free body diagram, draw the diagram. The second part is inertia. Okay, so we can start taking the inertia for, let's say, element 1. So inertia for element 1 is we have this hollow, which means we have these two diameters we need to subtract. So the outer diameter, so pi over 3 over 2, I will use diameter. So diameter outer minus diameter inner with power of 4. Okay. I hope you get why is pi over 32. 32 is because the original will be this, right? This is the original. So this will be from this d over 2, and that's what we have. Okay. So hope it's clear. So let's use these formulations, and we can put all the informations. So the outer is 50, so 50 with power of 4 minus 30 with power of 4. This is millimeter with power of 4. But since our torque is on meter, so I will also convert this to meter power of 4. So if we compute this, this will get you around this number. Okay, and then the inertia for element 2, which is the solid one. So this will be pi. This is the 50, right? But also I will convert to a meter. So this will be 6. Okay, inertia done. Okay. The second part is we can go for the twist. Okay. So twist, remember we have T, L, G, and then inertia. Okay. Remember for your quiz, chapter 3, we have E, F, L, A, or EA, right? This is the counterpart, the modulus. The force is torque. Length is the same length. Area, inertia in the twist angle. So they are basically similar. Okay? So, and how we can use it is basically the same. The difference is the twist angle we rotate. The elongation is we have extensions. Okay. Okay. Let's use this. And suppose that we have, let me write again. Suppose that usually we can compute this L over GI, and we can say this is as our small f. So for element 1, we have all the information needed. We have the length, we have the modulus, we have the inertia, so we can just plug in. This is to help our computation, so we can compute F1 like that. So this will be L1 over G over inertia 1. L1 is the 400 millimeters, so I will write 0.4 meter. And then G is 26 gigapascal. I will write that is let's say multiply with Pascal, okay, because I would like to have in a meter, easier in Pascal. And then inertia is 5. This will be equal to this number. But basically, you don't need to be worried about the units on the F, because this is simply calculation in between. Okay, so not necessarily important to the final results. But it's it's for your own calculations. And we can do the same thing with L2. This will be 0.8. Same modulus. And then this will be 6. And the result is 5. So we have F, we have all the information, we have the T, and then we need to add the compatibility equations. Okay. So geometry deformations that we have is because they are attached to the wall. So the twist angle between element 1 and element 2, they both need to be equal to 0, okay, because it's attached to the wall. So these assumptions make us, we can write that 0 is, okay, or F1 T1 plus F2 T2 equals 0. F, again, this is the same F with this twist angle. So we can rewrite, and then the T1 and T2 we can have from the equilibrium. We can use both ways. We can find the T1 first or T2 first, but eventually we'll get both torque. So let's say we are computing based on the, let's say we exchange the T2. So this will be F1 T1 plus, this will be T1 minus TB. So let's simplify this. So T1, this will be F2 TB, and T1 will be F2 TB over F1 plus F2. Well, if you like, and sometimes I also did that if I have the exam, all this F1 and F2, you can basically, you can put everything in, let's say in variables, into these equations directly, into these equations. And then you can input all together in one equation. But if it seems too big or complicated, like too messy, you can calculate one by one, just to help you out. Okay. And basically, since we have all the information needed for the F1, F2, and then for TB is this time. So we can put all the information and we can write that the T1 is around 6351.4 Newton meter. And then we can get the T2. This will be negative 3648.6 Newton meter. So this negative means, this negative sign means this will be going that way. Okay. It should be, but because we already make this assumptions that the T2 is the same with the torque B at B, so we just keep as it is. Okay. But we know that from this negative signs, this will be the opposites. So we have T1, we have T2, and from this T1 and T2, we can compute the tau max. Okay. So the first formula that you need to remember is the twist angle, this one. The second formula that you need to remember, or at least you know how to use it, is the tau max. Tau max, for example, for element 1, this means that the torque 1, of course we only need the value, no need to know what the rotations looks like. And then this will be the radius, let's say radius 1 divided by the inertia, okay, just that. And this is like most likely to be asked, right? So we can use the information given, or I think we can just put the information, just put the number, and we get the result is around and do the same with the element 2, means that this is T2 radius 2, and then inertia. Don't forget that this is radius, not diameter. So you need to divide by 2. Okay, this will be equal to and now we need to calculate the rotations. So rotation at B, or the phi B. If you look at the picture here, if we cut only the only B and T1 or T2, we get that this TB, or the phi B, will be equal to the phi 1. Okay, because here if we look, if we cut on the element 2, this 2 will be equal. So we can imagine that if that is happen for phi B, it means that this will be the results. Okay, or you could also do the same thing and make it the phi B is negative phi 2. You will get the answer maybe different, or perhaps different in signs. I think it's still okay, because we are not that strict with the rotation, as long as they are consistent, canceling each other. Okay, should be okay. So this should be okay, and if we compute this will give you 0.183 radians. Okay. You could use the element 2 as well, but you will get the same result with different value. I mean, this different signs, but it should be okay. It should be okay, either positive or negative. It should be okay. The answer should be okay. So there are many other, or perhaps some other questions that quite similar. So I hope you can get it correctly. Later I will upload the notes and exercise after we finish the class. So let's see the other questions. Okay, let me continue. So this is another question, and this will be, I think, it's quite similar. The difference is we have two external force at B and C, which give you different equilibrium, but the procedure, the steps will be the same. So first, going for free body diagram, equilibrium, and then we can go for either inertia or finding the twist angle computations, the F. Okay, and we can have the geometry of deformation, use compatibility equations. You can have now we have three elements, so we have phi 1 plus phi 2 plus phi 3 equals 0. And then in between of this information, we can substitute, solve the equations, and then we get the results for the torque, the internal torques, T1, T2, and T3. Okay, same thing. So I think I will keep this for you. So you should try this. Okay, you should try this. So let me go for. I think this will be also the same. Okay, let me focus on the other question. So that's this one. Okay, this is another method, basically the same, but the previous one, by default, it will be the force method. This is the displacement method. So let's focus on that. So we have the shaft AC, and then we have length, we have the titanium alloy, we have the aluminum alloy, and yeah, they have their own modulus, diameters. Okay, they want to compute the rotation at B, which is at B also we have the torque, the external torque, which is 5.6 kilonewton meter. And then maximum shear, so basically same questions all over again. Maximum shear for these three elements, tau max 1, tau max 2, tau max 3. So how do we start? We start with free body diagram, and as we can see, since we are clearly see that it's only having at least most phenomenon happen in the middle. So we can cut off this part, which consists all the element, right? Element 1, 2, and 3. Element 2 and 3, they are on the same sections. The element 3 is the outer layer. Element 2 is the solid shaft inside. So we can basically say that we can have this diagram. Let's say this is element 1. And this is element 3. Element 2 will be inside. And then this will be B. And then we say that we have, this is the external torque TB. And then suppose that we have, okay, I forgot to get, this is the x-axis. And then we can imagine, let's say T1 is over here, okay, goes that way. Oh. And then T2 and T3, both are on the same section. So I will get you this T2 perhaps, and then the other one is T3. Okay, on the same sections, okay, on the same sections, because they are basically outer and inner layer of the shaft. Or if we name it, this is 1, this is 2, and this one is 3, right? Okay, so everything have done here, and don't forget we need to write the equilibrium based on this, that T1 plus TB equal T2 plus T3, okay, or TB is negative T1 plus T2 plus T3. Okay, the difference between the displacement method and the previous force method is the way we write the twist formula. So we can start, as always, we can start taking the twist angle. This is T, L, G, I. Okay. For the displacement method, we are going to rewrite this in terms of T. So T is angle G, I over L. Okay. And suppose that this is something that we can compute at the beginning. We can rewrite this as SK, small k. So we can write T1 is phi1 and K1. And since K1 is something that's supposed in the given in the information, and we can compute the K1 first. So we can compute the K1, which is G1, I1, and L1. Actually, we can compute the inertia first, but I forgot to write that, but let me just go directly to the K. So this will be G1 is here, okay, is already given here, 40 GPa, and then we have the D1, okay, element 1 is solid, so we have 50 millimeter for diameter, and then the length is L1. L1 is 1.8 shaft AC. So this is titanium. So 1.8. Okay. 1.2. Okay, we have everything. So we can compute. And let me just write this. Inertia is I will go directly for the result. This is 40.9. And then do the same thing. This is still solid shaft. This is G1, G2. Okay, and this will be around 20.45. Oh wait, it's not Newton, millimeter over radian. And then K3, this one is the hollow. So this is G3, I3 over L3. So pi and this is resulting in 26.57. Okay, so we have all the K, and then what else? Okay, we can write that since this is the orientations for, or let's say if this is on the same sections, that the change in B will be equal to the change in 2 and the change in 3 because they are on the same sections, right? And because they are attached on the wall, that T1 plus T2, or here's phi, this will be equal to 0, so T of pi 1, we can write that this should be equal to negative phi. Or let me just write this 2. Okay, this 2 should be enough for our calculations. And because we have this, then we could write this equilibrium. Okay, we can write the equilibrium. So the equilibrium, the difference is what we solve now is the torque. The previous one we solved the twist angle, right? So we solve this. So let's say we write TB equal negative T1 plus T2 plus T3. So TB or TB is what? 5.6 or 5,600. So 5,600 Newton meter is, T1 is this. So we can compute that. Okay. And then from what we have here, we have that phi1 is negative phi b is phi2 equal phi3. We can substitute all into these computations. So this will be, because it's negative, so we have a positive. Okay. And then we can compute the phi b is 5,600 K1 plus K2 plus K3. And all this K1, K2, K3 we have from here, substitute and then compute, and we get the twist angle B, which is 0.06369 radian. And then the same thing we get for T1 will be, or this will be and T2 will be, and T3 will be the same. Okay. So all we have informations, we have all T1, T2, T3, right? And then the second part is the maximum shear stress. So when we get this equations, we solve the equation. The rest of the questions, we just put the number, compute using calculator. So I think very easy. But the difficult part is on the beginning. Okay. So tau max will be T1. And then radius 1 divided by inertia 1. Compute this and you get this is around 100.15. And do the same thing for the second. And I think my suggestion is that maybe you can write the inertia at the beginning to help to compute this. So we get all the informations correctly. Okay. So this is the difference between the previous example and this one. The difference basically how we write the equations. Okay. So usually in the displacement method, we are going to solve this T equal twist angle, but the force method, we are going to write the twist angle equal the T, okay? And then we solve that as well. Okay. But in any case, both works. Sometimes you can choose. Okay, you can choose which method you prefer. If it doesn't specify specific method, you can use the force or displacement method. Which one you think may be preferable for your computations. Okay, so that's the I think mostly chapter 4. Okay, we have the force method. The second one we have the displacement method. And the rest of the exercise I have put in the Moodle, I think around 30 to 40 minutes video, 3 or 4 questions, I forget. But that's the chapter 4. Now we move to another sections, the other chapter. I think I wrote last week that will be chapter 5. In the old edition, that is chapter 5, but if you read the new edition on your textbook, it should be chapter 6. Okay, so sorry for that. Okay. But what we discussed is actually the same. So it's chapter 5 old edition, but now the new one is chapter 6. So this in the books, the new books, you have this problem 6. Okay, problem 6. So now let's start with the something very, I think this one should be okay. This is pretty similar to what we have in the, I think in the statics or in the beginning of our discussion in this semester. So I think I will just go for our focus, okay, which I expect you to get these questions correctly. So this is also similar, this one. Okay. So the final results, okay, aside finding the internal shear force or the bending, is to sketch the shear diagram and the moment diagram. And I think since we have the, let me check. Okay, and I will focus more on the, if you remember, if we have only concentrated force, then the shear force may be having a constant and the moment having a quadratic equations. But here we have a distribution load. So we are going to expect that at the at some point, perhaps we have a quadratic and then we have a cube, okay, if you remember. So this will be, so first thing is we can find the equilibrium. So I think, let me copy this, okay, for a while, just to show you the equilibrium. So we have a rectangular shape of distribution of load. We have the external loads 30 kilonewton. We have 30 kilonewton per meter distribution load, and the total length is 6 meters. So precisely at the middle of these beams, we have the concentrated load of 30 multiplied with 6, which is 180 kilonewton. Okay, that's at the beginning. And then we have, and suppose that we only care, no matter the pin looks like, we only care the y-axis, okay, for the beams. So we care on this AY and CY. Of course, you can write like some maybe if they have the horizontal, you can write the horizontal, but it doesn't really make difference, okay? Because at the end of the day, this vertical axis that will be our focus, because we want to make sure that we can confirm the shear and we can confirm the moment, which is basically they are affected by the force on the vertical axis, right? So what should we do next? Taking the equilibrium. So equilibrium. So sigma moment, and we can do from C, we can do from A, doesn't matter. Let's say we do from C. So AY, and then I think, let me make this positive over there, rotations. So AY multiplied with 6, and then we have negative 30 kilonewton multiplied with 4, and then the same negative, and then 3, and what else? I think enough. So this is equal 0. So AY we get compute everything. We have 120, 550 divided by 6. This is, so 660 divided by 6 is 110 kilonewton. You can use the other moment to get for Cy, or you can write the sigma f of y-axis equals 0. So Ay plus Cy is equal to 10, right? 180 plus 30. So and Ay is 110, so Cy will be 100 kilonewton. So we have now all the reaction force. Okay, what's next? Next is we need to compute what we have in the diagram. For example, if we are, so we always start from, let's suppose that we are walking from the point on the left. Okay, suppose this is you. Okay, we are walking. There's nothing much happen aside from we have a distribution load, okay, along the 2 meter. So we have distribution load here, and suddenly we have something on B. We have another external load, okay, which give you jump in the diagram or the curve. And then after we get 30 kilo, then we are walk again, and not much happen, but we have only distribution load. So at least we have two points, okay, or two sections before B and after B. Okay, because at B we have additional forces. So we can write here, perhaps taking the interval at 0 x 2 meter. Right. So we can start with, we have Ay, which is 110 kilonewton. So we can start with the Va at 110, because that is our reaction force. And then we have distribution load that is going down. Okay, so first is we have this much force, 110, and then as we move here, we're getting loads. So from here, we get linearly going down. Okay, if you get that, or if we write in the equations, okay, maybe we can continue after this. Okay, so let's continue. I will develop the graph while let you see the equations on the right side. So I think it's best to give you what is happening in the graph. So let's do that. So we have, this is the graph, and I will make it with the same proportions with the beams. Okay, so we can confirm directly. So perhaps in the exam, I will prepare the graph like below the diagram, so you could take the axis, prepare it from the point on the left on the beams. Suppose that this is we start from, so suppose that this is V. This is a kilonewton, right? And this is X. So we start from A. So let's say this is A here. Okay. So A, we start from AY, which is the internal force, which we can compute that as 110, right? So we start from this 110. So put, and I don't really, if you have maybe different scale or ratio or proportion in the graph, I think it should be okay as long as you wrote the correct number or the correct equations. Okay, so let's say we have 110. Let's say we have here. Okay, this is 110 kilonewton. Okay, and then what will happen is along the line, when we move from A to B, we are actually, if we look at this, we know that the P is basically the first derivative of V, right? So this will be dV over dx, which is, in our case, because it's going down, it's negative 30, okay, kilonewton per meter. So when we move from A to some point X on, let's say B, 2 meter, so we are going to have a load that is 60 kilonewton per meter, or 60 kilonewton. So at P equal to, or suppose that we have V, which is negative 30x. Okay, this is our equations. So at V x equal to, this will be negative 60, which means that at x equal to, which is here, so let's say we have, this is 2 meters, I will directly write this as our information given here. So this will be x equal to. Okay, so that will be 2. So from this 110, we are going to minus how much? Minus 60. So at the new calculations, we have a, this will be, we move 60 going here, perhaps around this number. So I will give you, let's say this is 60. So 110 minus 60 is 50. So we have 50 kilonewton here. This is 50 kilonewton. So let's say this is our V at B. So at VB, this will be 110 kilonewton minus 30 multiplied by 2 will be 50 kilonewton. Or to be precise, our V is not only negative 30 because we have V0 is 110. So our equation on Vx, I haven't write the full equation. Our Vx is 110 minus 30x. Okay, and I think we don't need to write this. Maybe just write this whole formula. Okay, this is much better. Okay. So VB at B at 2 meter is 50 kilonewton. So it's reduced 60. Okay. And remember also that the Vx is actually our first derivative of the moment. So later, for the moment diagram, we can integrate this 110 minus 30x. We can integrate one time, and that will be our diagram for the moment from 0 to 2 meters. Okay, but let's put that aside. Let's check the after the 2 meter. So we can have at 2 meter less x less 6 meter. What will happen? Here we have BC, which is this. We have distribution load, but we have 180. But first we have at point B 30 kilonewton. So let me draw that at B. So at B we have 30 kilonewton at that one, and then we have distribution load, and then we have this is perhaps at 1 meter here, and then we have another one which is 3 meters. Okay, and then at the end we have, I forgot to write AY here. Let me write AY, and here we have CY. So this will be B, this will be D, this will be C, right? Okay. So we first take a glance that at VB, we have additional negative 30 at this VB. Now, of course, at VB, we have 50 kilonewton minus 30 kilonewton. So we have, this is additional VB. Or to help you understand what this is, maybe let me write at B, we have external force that equal 30 kilonewton downwards. Because if I write delta VB 30 kilonewton, it will be very confusing for you. But let me help you to write this. Okay, so here at 50 kilonewton, so we move from A. Now we have now at hold down at B. So at B, okay, so if you see this, since we have another external force, what will happen? We have a jump. We have jump. So from 50, we take minus. So here, about 30 kilonewton. So we have, this will be 20. Okay, so we have here 20. So we hold at B. So still hold here, maybe up until this one, and this will be equal 20 kilonewton. Okay, and then we start moving again. We start moving to, so this one is B, this one B. So we start moving up until this D. Or let's say this is because we know at we can write that dV dx is P of x is negative 30 kilonewton per meter. This is the distribution load that is here. And then we know that at C we have another conditions, right? Another conditions. And okay, now we can write here, oh, sorry. Since we know that Vx is this, we can apply this to get that when V is 0, so we can write this. So 3x is 110 and x is, how much is this? Vx, let me check to make sure. 36.6, 36.6, 36.6. 6.6. Okay, 6.6. Okay. Anyway, we have 30, and then we have at C. So we have 20, and then we move 1 meter, so we have negative 30. So this one is, we have negative 30 x, but start with a we start from 20. Supposed to be this, right? 20 minus 30x. So suppose that this part of the, let's say this is D, and this is C. Okay, let me check if I have. Okay. 30 kilonewton per meter. If I multiply this, it's around, so 4 BC is 30 multiplied by 4 should be 120 kilonewton, right? If we compute only that part. So 30, so 20 minus the 120, it should be negative 100, right? Because it's going down negative 120. So I think I missed out here because I imagine that this is, so let me erase it. This is confusing for this part because I should compute in this whole system. So we need to compute this, like for example here is 4 meters, so this will be negative 34, this will be negative 20. This is the how much it goes down. Okay, so we need to move negative 20, so which means that we are expecting, I think I need one more space for the moment. So this is only the shear force. So this should be having another layer here, which has the 100 maybe here for negative 100. Because we have 20 and then minus 120. So this will be goes down, maybe up until that part. So that will be our equation for that part is our Vx is negative 20 minus negative 30x. Okay, so at V equal x equal 4, oh, this will be V2. So V2 is 20. So V2 is 20. So this is not negative 20, it's 20. But it should be 6, right? It should be 6. So it should be 180. I think I have something missing here, but this is, the graph is correct, but why the equation seems I have something missing here? So it should be, this should be 6, right? It should be 6. So that means, okay. Okay, suppose that this is the, let's say this is I put another 0 here. This is, so that this will be 4. My equation will be true. So this will be 20. This will be 4. For this distance, so 0 and 4 is the distance. This will be true. So well, for V at distance 4 from 0 to 4 on this 2 to 6, then this will be equal to negative 100, and my equation is true, right? So that is if we start from 0. So if our V is 0, 20 is equal to 30x. So x is 20 over 30. So 2 over 3. 2 over 3 is 0.6, right? Yeah, 0.67. So this x means additional, that will be this x. Okay, this is x. Okay. So the point here, then this is, I think, important to take this, the point, because it's changing the positive value to negative value. This is at 2.67 meter, okay? Okay, so we have the V, okay? Now we are going to translate this V into our moment. So let me duplicate this page. Copy page. And then paste page, okay? And then let me erase on the right side. Okay, you can refer to the previous one. I will focus now taking on the moment. Okay. So I will put all of this in right side. No. this. I'll put up until here. Okay, I will make another graph. And make it the same scale to help understand what is really happening. So this is x, and now this is the moment. Moment will be in a kilonewton meter. So what's happened is at this point, let's say this is 2 meter, and we have this 2.67, which is important. Let me write again here. This is 2, this is 2.67. Okay, I think I wrote everything correct. Now we move from 0 to 0.2. We have a positive slope, right? We have a positive slope up until 2 meters. Okay. So from A to B, we have a positive slope. And what is our slope? Slope is basically, we can write that the Vx for 0 to 2 meter, this will be our graphs, right? So m, this will be 1110x minus 15x squared. Okay. So that's what might happen, but I'm pretty sure that you don't need to write or graph the curve accurately as long as you know the exact number. Okay. For example, what we want here is at x equal 2. So at x equal 2, we can compute this. So this will be 220 minus 60, which is 160, right? So that means at S2, maybe here, this will be 160. Is this maximum? I think it's not maximum. Maximum is at 2.64 when its gradient is changing. So at this 0 to 2 meters, we have this graph. Let me write here. That's graphs. And then we know that the 2.6 will be our maximum point. So we can add here that this will be giving you the maximum. And then at the end, we have this graph, okay? So this doesn't really, we don't need really to worry much about the graph as long as it's matched up with our equations. Oh, I know. What I did wrong here. Okay, let me make up this, just a little bit mistake, but it's still true. It's still true. So if we make it, this is v of 2. So we need to start off with the 50. So 50. So we start off with 50. So v2 is 50, or 80 to be precise. 80 is 50 and 30. Okay, so it means that 50 plus 30, and then this will be minus 30x. So v4 is 80 minus, or 6, sorry. So this will be the same. This will be negative 100. Okay, the same. This will be, should be 80. I forgot to add the 50. And this will be directly get to 2.7, okay? But you can do like I did. Sometimes it's much more easier. You can try to make this another 0. Okay, I hope you get what I'm saying. Although I think you feel confused about this. I know. Sorry about that. But let me continue this part. Okay. So for the second part, if we want to, let's say, check up the equations, so we can start from the Vx, and then we can get into the M. We take the integrations, and this will be our results. And we can basically, if we check at x equal 6, what will happen? This will be 6 squared, right? So we have how much we have here? 540. So it should be what? Should be how much this is? Or perhaps maybe not this one. Maybe let me compute this one first when we have the maximum. If we check the maximum and get into these calculations, we have 166.66. So that means this maximum here is 166.66 kilonewton meter. Okay. Oh, I forget to finish off the graph on the V, because this is negative 100. Precisely, we have Cy, which is 100. Right? So we add 100 and we get back to 0. So this is 100. So we have in the equilibrium. So our force, they are matched with our system. So I think if the questions only give the illustrate how the curve will be, I think if you draw like this, just taking which is the usually the important one will be the starting point, and then the x. I mean, the result for when is the gradient change, the slope is changed, which is 2.67, and the bending maximum, which is 166. Okay, that's, I think, all the important or necessary things. Okay. Okay, what else do we have? I think we can move for another. Just let me check. Okay, maybe one more typical question from this beam. Okay, we have either this or this. I think this one's same rectangular shape. Let me give you this 6 for. Oh, it should be this one first. The previous one is, I think, more complicated than this one. So let me get this. 6, 4, 9. Okay, let me crop this, or let me copy. And then crop, that will be. Okay, we have a triangular shape. Question will be the same. We need to draw the shear diagram and the moment diagram. Okay, we have a 3 kilonewton meter, and basically we can find the concentrated loads, which is supposed to be, if this is 180, we can divide by 3, which is 60, 60, 60. So 60, 60, oh, suppose this is 120. So this will be the concentrated load, right? So 3 multiply with 3 kilonewton per meter multiply with 180 millimeter or 0.18 millimeter divide with 2. Let's say we have 1,500, multiply this, should be around 270 Newton, right? Okay, and then we could take the moment. Oh, I think I will write the moment here. Moment. Suppose that we have these two pin, AY and DY. And suppose we start with D equals 0 and take that positive. So we have 270 Newton and then 120 millimeter. So we have 0.12 meter, and then oh wait, not 0.12, this should be to D, so 18, sorry 18, and then 300 Newton, 0.06 meter, and then plus AY, the whole thing is 3, right? So 0.3 equals 0. So calculate this, we have AY as around 222 Newton. And then take sigma F. So we have AY plus DY minus 300 minus 270 is equal to 0. So dy is, if we calculate, we get 348 Newton. So we have ay, we have dy. We can write here that this will be 222 Newton, 348 Newton. Okay. So we can start off by taking the shear diagram. We can take the, let's say, each sections. For example, we can take the sections AB for the triangular shape. This one is, I think, quite interesting. If we take this, and suppose that we are taking some x. So this is the more, I think this is more delicate than the one I give you, which this one have more steps and procedure that you can follow. But you can actually skip all of that and focus directly to the final results. Okay, suppose we have this, and this will be the x. Let's say this is x. So this is for AB. Okay, for AB. We have AY, this AY. And here we let's say we have V1 and we have M1. And we have another concentrated load, which is here. We are defined with this one is 2/3x. This is 1/3x. And then from the whole diagram, suppose that we have the same ratio. So suppose that we have, this is y. Okay, let's say that is y. We can use the triangular ratio. So y/x will be equal to 3/0.18 meter. Okay, because they are the same triangle. So y is 3/0.18x. Okay, that's for y. So the concentrated, let's say the concentrated forces, let's say F. Okay, so F is 3 over multiply with x, multiply with x, and then multiply with 1/2. So this will be 3/0.36 x squared. So that will be the F. This one, F, the concentrated load. Okay, what else? Yeah, I think we can make the equilibrium. So AY minus 3x squared over 0.36 minus V1 of x, this is 0. So V1 will be 222 Newton minus. Okay, so you could do this as well for the previous questions. Okay, so I haven't give you like the each one of it, because the rectangular is supposed to be not that as much complicated as the triangle. So we have this, and we have the M1. Take the sigma moment. Suppose at x, which is at this point here, so this is 0. So AY x minus 3x squared over 0.36, and then this is x over 3. So m1x will be 222x minus 3 or x cubed over 0.36. Okay, I think this is more procedural that I think it can help you to understand how we get this. Okay, and then for BC, we can have this here. This is for BC. And suppose this is D, or let me write this as BCD, okay, BCD. So this will be dy, and this is C. Okay, this will be 300 Newton. And this will be V2 of x and M2 of x. And we have here is the 60 millimeter. And we have here, which is 240, but I will take this x, so this will be 0.24 minus x, okay, meter. Or here's maybe not 60, 0.06 meter. Okay, do the same thing. You can take the sigma f, so get V2 plus dy equal 300, or V2x is negative 48 Newton. And then take the same thing. This is equal 0, so M2x minus 300 0.24 minus x plus 348 and then this will be, we plus this and we get this will be 0.3 minus x. This is equal 0, so M2 will be negative 48x plus 32.4. So we have M1, M2, and then one more is basically we can cut this open, this one here. So for CD, okay, so we can have a CD, let me write here. So this is only dy and the V3 and also the M3. And this is practically the whole thing minus x, okay? So the whole, 180 plus 120 is 300, right? 300 millimeter minus x. So x will be this, the movement, okay? So we use this sigma Fy. So V3 of x will be dy. And then the M3 is getting from the sigma M with respect to x. X will be at this point here. This one is x equals 0. And I will write the final equations. Okay, so we have all the conditions for V1, V2, V3, M1, M2, M3. Translate this into graph, okay? I think this will be much procedural, easier to understand. And hopefully you can get the idea. So basically, this is I think last sessions. So I haven't wrote the graph, but I will give you in the notes, okay, in the notes. So I hope you can look up your notes. So basically, what we did, or what I'm suggesting to for you, is you can imagine you start on this A, you start moving to the right, okay, moving to the right. So if you cut down the beams, your distance, your x will be, the perspective should be from the A, which means that for this one, we start this one x, and if we take the other part, if we cut through the other element, we are also imagine that this is the one that we are just left. Okay? So we have distance x here. So we say that, okay, this will be the 0.24 minus x. So this will be 0.24, the whole thing, and then this minus this x. Okay? And similarly for the last one here, the last piece, okay, we cut open also. So how do we know that we need to cut? When we have the external force and the load. For example, this one, we have, okay, one section, cut, second section, cut this one, and this one, cut. Okay? So we have three sections, and then we cut. Because at those intervals, we have external loads. That the external loads might interfere our graph. And usually, when this happens at the C, you will see that the point will be jumped. This is going down, so you have maybe point here, and it's going down at those C point for the force, for the shear force. Okay. So then you can transfer to the graph, or if you want to draw the graph, let me copy this. Hopefully, I have time. So let me erase all of this. Okay, so first is we have this is the F. Well, let me just remove this, okay? Because I need to make sure that we are having two diagrams, and then we need to find when V is 0, for example. So we start with the 222 Newton. So we maybe here 222. This is V. This is X. Okay, and then this will be point C. This is the last distribution load, and then when V is 0, we can have, for example, Vx at the V1. Let me copy this. So when it's 0, we can have solve these equations basically, and we get that the x will be around 0.163 meter. So this is when the x is 0, when v is 0, which means that v will be 0 at this 0.16. So if this is 0.18, 16 is maybe around here. So since we have the quadratic equations, so we are going to have a quadratic starting from 222 going down. Okay, maybe I will draw correctly. So suppose that like that, and then stable. And then at the V1 at 0.18, we can also get the number. You can compute this. So we get some number over there. So take minus, and then we are going to take at this 300, we're going to take going down here by 300. And then stable, and then at this end, we get 348. So distance 348 here. Okay, it should be matched with all the numbers. If you want to confirm, you can confirm, for example, 0.18, what will be the number here? And then minus 300, stable, and then plus 348. So you need to get back to 0. Okay? That's how you confirm that you are correct. The graph will take you to 0 at the end of your movement. Okay? And for the moment, the same thing. You have the moment equations. You have the x. You can match up the x with the graph. Okay, I think I will finish off this after the class. I will give you the notes. Okay.